so we figured out that at point P, the estimated rainfall is 0.63 cubic inches. And so that's what nearest neighbor interpolation is that if you fall within the cell of the information that you've collected, then you fall under the umbrella of information that goes with that. Now, again, P could be on the other side of a mountain, or P could be at the top of a cliff, or P could be a lot lower in the valley and have much more water. There could be a lot of things that are going on there that we don't know. I'm assuming that the people who placed the water gauges took in mind the different extremes of the terrain, and so as a result placed the water gauges in the different extremes and the middle grounds. And so the reason for the clustering for some of these might be because there's a varying amount of terrain that's happening in that area. You would hope, but who knows? Because we don't know. Okay, so that's one way to use Voronoi diagrams in an informed way. Another way is called the largest empty circle. It's typically referred to as the toxic waste dump problem. I like to think about it of like if I were a business person and I wanted to figure out where to next place my next chain restaurant or shop or whatever you have, or a clothing store, right? You would look at the Voronoi diagram of the places of business that you already own. So you can see here on the left, that's what's going on. And then you say, well, where is the desert? Where is the place where we have a big open space, right? Going back to the map, we can easily start pointing out the places where there's very few and far between airports because we've got these larger and larger bubbles. So that's the idea with taking these other Voronoi diagrams, is we're trying to figure out where is the largest need for whatever we think people need. So what we do is that the center of this largest circle you could create is always going to be at a vertex. So we're talking about a circle that you can create starting at one of the vertices of these polygons. And remember, the vertex is where all of the edges come to meet in a corner. So you start at one of those vertices and you build the bubble out until you hit another site, as you can see with the green circle. So find the coordinates of the center and the radius of the largest empty circle, LEC, in the Voronoi diagram. So we're looking at this Voronoi diagram and we only have two vertices, and those vertices lie on 4, 3 and 10, 3. So those are our two options. So I might even represent them with two different colors. So I'll call this one A, and A is 4, 3. And then I'll call another one B. Now, we could look at these 2 points and have a pretty good guesstimate of which one is going to create the largest bubble. But for the sake of mathematics and for the sake of understanding that we know that it won't always be this easy, we need to talk about what happens if it's not easy to just see right away. Well, we need to calculate the radius then for the circle that could be created from that vertex. So the idea is that if you expand the distance from that vertex, and then you've got another site over here that's expanding a circle that's centered at the other site at the same time, is that your radii will always be the same. And then once those radii are exactly the same is once they start to touch. And this is where your perpendicular bisector comes in, this idea of splitting the space in half. So we need to talk about the two circles that are being created at each point, the vertex of our edges, and then one of our original sites. And as those circles expand, we want to know when are those circles going to touch? When are those two cells going to interfere with each other such that they start to create that line between the two bubbles? So we need to find the distance between each of those vertices and the 3 points that created that vertex. Because remember, we talked about this idea of triangulation and about finding those perpendicular bisectors of all of the side lengths, and where those 3 meet is actually one of your vertices. So, for instance, the point 4, 3 is made by triangulating A, B, and C. So if I wanted to find out what the radius of that circle was as I expanded out, I could talk about the distance between that vertex and A or B or C, because they will all be the same, which is the point of finding these circumcenters, is that it is the only point in this entire map that is equidistant from all three of those points. So if I find the distance of the vertex to A, it'll be the same as the distance from that vertex to B or to C. But I don't care about the distance that's the complete distance that's coming out of the vertex. I'm talking about the distance as these two circles expanding at the same rate intersect with each other. And when are those radii equal? So I'm going to find that radius or that distance between the vertex and B or C or A, and then divide it by 2, because that's when those distances become the same. So I'm going to take the point 2, 0, because that's the easiest of all 3 points in my mind to find the distance between, I can't label these guys points A and B because other things have already been labeled A and B. So I'll call this guy Y and then this guy X. So then the distance between X and A, which is 2, 0. Remember, your distance formula is just the Pythagorean theorem in disguise. So we've got, and it's also in your formula packet, the square root of, and remember that we're finding the distance between your X values and the distance between your Y values. Distance always means difference. So we're subtracting your X values. And it doesn't matter which order because we also are squaring them. 4 minus 2 is 2. 2 minus 4 is negative 2. Squaring either of those will result in the same number. And then we add, and then 3 minus 0 squared. Four minus 2, 2, 4 plus 9 is the square root of 13. I'm just going to leave that distance as that for right now, because remember that we're trying to find the largest circle that you could possibly make. Remember, we're looking for that big green circle that comes out of it. So this is a square root of 13 as a radius. So now if I go over here and talk about the point 10, 3 and find the radius there, if the radius from that vertex to point B, C, or D is larger than the square root of 13, then we know that that would be the largest, what is it called again? The largest empty circle. Okay, so the distance, I'm going to do C, which is 6, 0. So then the distance there is 10 minus 6 squared plus 3 minus 0 squared. 10 minus 4 squared is 16 plus 9, which is the square root of 25, which, yes, is 5, but I'm going to leave it as that for right now because it's easier to compare the square root of 13 and the square root of 25 as it is to compare the square root of 13 to just 5. Here, it's clearly obvious, as it was clearly obvious in the diagram, that Y, that point 10, 3, is going to give us the largest empty circle of this Voronoi diagram. So as a result, so we found the center, it's 10, 3. We found the entire radius from that center out to each vertex. Sorry, not vertex, site. But now we need to take into account that the moment that these guys, that these two bubbles are expanding at the same rate and that they need to have the same radius in order for that to be the largest distance that they can go. Oh, well, I guess the largest empty bubble would be a radius of 5. So what I was saying about the expanding circles at the same rate is actually a moot point because all we need to know is the radius of the largest empty circle, and that's it. So the radius of the largest empty circle is 5, and the center is point Y. I believe this diagram was given to us earlier in our notes, and it didn't give us a context, but those are, we could be talking about restaurants or chains, or we could be talking about delivery services. If you are somebody who's working for a delivery service like Uber Eats or Deliveroo, you could create a program on your map, or maybe Deliveroo and Uber Eats could create a program on their app for the drivers that creates a constant awareness of where each of the drivers are and has a constant program running of where all of those drivers are and creating Voronoi diagrams of those guys. And so you can then pull up that app on your phone. I don't even know if this is a thing that should exist, but one of you guys should invent it. Maybe I should invent it, where you can pull up your phone as a driver and be like, well, this is the largest empty circle on this map. And if I go and move myself to that largest empty circle, then maybe I would get more hits because I'm placing myself in a place that has a greater need, right? I'm not going to go center myself around all the other drivers where all the other cells are so small because so many drivers are so close together. I'm going to go where drivers aren't hanging out. Maybe there's a reason why they're not hanging out in that certain area, though. Like maybe there's not a whole lot of customers who buy from Uber Eats or Deliveroo in certain areas. But that's the real life situations coming into play here. Okay, so that's it for your notes today. There was just a lot of me talking and spitting ideas at you. This could be something that's really cool to do for your IA. Whether any of the things that I've just said in our previous 2 lessons has hit home with you as something that's like, oh yeah, whether it's the creating an app and programming and finding out how to always ping and create a constant running Voronoi diagram of drivers with Uber Eats, or whether you want to talk about restaurant chains and where to place them, or if you want to talk about airports, or maybe you want to talk about the effects of hospital distances with coronavirus and death tolls, and trying to see if maybe that those death tolls are, which is really morbid, but it would be something that would be really interesting to look into, of like where there are places where there are hospitals closer together, are people surviving more, are people being treated more, and make those connections. A lot of times we also talk about with Voronoi diagrams the areas that you can create from this, talking about a comparison of size that a certain place is or a certain thing is administering to. For instance, like a hospital, the larger size cell you have, the larger area cell you have, the more people potentially you are caring for. Whereas somebody that has a smaller cell, depending on the density of the population, which could be another mathematical equation that comes into play. So there's just a lot of really cool things that are out there. I would encourage you to keep digging about Voronoi diagrams, looking at the cholera epidemic, looking at Pixar and how they use it in their art and why. There's a lot of really interesting things out there. Okay. We have 1 review session scheduled before our unit exam. Period 6 is tomorrow, and period 8 is next week after the long weekend. I would like to have another optional review session. That's going to be an after-school review session the day before the test, but I don't want to do it if nobody's interested. So let me know if you want to do an optional after-school additional review session besides just the 1 in-class review session, and I'll see what I can do.